Welcome to this episode of the Verilog Bench. Today we are going to be looking at the latest overview of multi-layer AHB. This is the top-level reading of DVI0045B, the current published issue of the overview. It is still an architecture document, not the full AHB protocol rulebook. So the goal here is to understand why multi-layer AHB exists, how the matrix is organized, and where it fits in the AMBA family. The date framing matters. The current published issue is still rooted in an early 2000s architecture step. The change history shows Issue A in March 2001 and Issue B in May 2004. So this video treats multi-layer AHB as an established interconnect idea, not a recent protocol invention. The motivation is straightforward. A shared AHB bus works well until several masters need real bandwidth at the same time. At that point, the bus becomes the bottleneck. Multi-layer AHB answers that by creating parallel access paths through an interconnect matrix while still reusing the familiar AHB transport model. The basic picture is simple. Each master enters the system on its own layer, and the interconnect matrix routes that traffic to the chosen slave. If two masters are going to different targets, both transfers can make progress at the same time. That is the key gain from the architecture. The implementation summary is decode, route, and arbitrate only where it is needed. Each layer determines which slave it wants. The matrix muxes the request to that slave port. If two layers want the same destination, the arbitration happens there at the collision point instead of at one global shared bus choke point. One of the most important benefits is per-layer simplicity. If a layer has one master, then the layer itself does not need the classic shared bus ownership machinery. That is why the document says these layers can use AHB-light style behavior, with the complexity moved into the interconnect matrix. The advanced options section shows that the matrix is flexible by design. You can keep some slaves local, group several low-bandwidth slaves behind one port, let several smaller masters share a layer, or use multi-port targets for high-value resources. So multi-layer AHB is not one topology. It is a family of scalable patterns. The worked example is where the ideas become concrete. One CPU has a dedicated path. Another CPU shares with DMA. Lower bandwidth peripherals can still sit behind an AHB to APB bridge, and a dual-ported memory interface shows why parallel access really matters. It is also important to say what this document is not. It does not replace AHB transfer rules. It does not define coherency behavior, and it does not serve as a scheduling or quality of service standard. Its job is to explain how to scale AHB-style access with a matrix. The overview takeaway is that multi-layer AHB improves available bandwidth by parallelizing access paths, localizing arbitration, and reusing established AHB components. It is a topology play, and that is the right mental model to keep as the series moves into deeper protocol videos. If this overview was useful, like and subscribe to be notified of future videos. Next, we keep the same multi-layer AHB document, but shift into the RTL and implementation perspective before we do the software view. To close, here's a glossary for the core acronyms in this video. AHB means Advanced High Performance Bus. AHB Lite is the single master subset used for simpler layers. APB means Advanced Peripheral Bus, and DMA means Direct Memory Access. HREADY is the signal used to indicate completion or waiting. The interconnect matrix is the routing fabric between layers and destinations. A slave port is the place where requests to one target are arbitrated. Coherent means different observers see the required consistent data view after updates have been made visible.